not least, it's our talk by Phil Yawman from DigiM Solutions. They actually are using magnets too, but not the same magnets, yes, for particle acceleration. So Synchrotron and and Tomography combined with AI-based image analysis is a characterization, non-destructive characterization that allows us to characterize amorphous solid dispersions. So that's what Phil is going to talk about specifically. About Phil, Phil has been with DigiM Solutions since 2020 and is currently lead product specialist supporting microstructure characterization of oral solid dosage forms with a strong focus on amorphous solid dispersion, which is, a part of what we are discussing today, specifically for bioavailability enhancement. Phil has a background in imaging, ranging from diagnostic medical imaging in the field of dentistry to nanoscale imaging and microstructure characterization in pharmaceutical industry. Phil is focused on application of correlative image analysis to the optimization of pharmaceutical formulation, design, and performance assessment. He holds a bachelor's degree in biomedical engineering from University at Buffalo and biology from University at Albany. Again, thank you, Phil, and I am personally interested to learn about this specific technology. Thank you. Welcome.
All right, thanks for the kind introduction. I recognize I'm the final barrier to everybody enjoying a well-deserved drink, so I'll do my best to be efficient here. So I'm presenting today on behalf of my collaborator, Dr. Tatiana Marcosi, who's a principal scientist in oral solid development at Johnson & Johnson Innovative Medicine. And I'll be presenting some of our recently published work on the application of advanced imaging and AI image analysis in advanced characterization of particles, in this case, spray-dried dispersion particles. So here we can see some cotton candy and a Nestle Milky Bar. So what do these two things have in common other than the fact that they contain sugar? They contain amorphous sugar. So here, the structure of the sugar has been altered in a way that it can actually increase the dissolution and in turn will improve the desired effect of sweetness. So what do these two things have that are not in common? Their amorphous sugars are very, very different structurally. So the cotton candy is actually composed of long filaments of sugar created by heating up and then rapidly cooling down the sugar, essentially to stop it from recrystallizing. Whereas the Milky Bar, which you could, before I covered it up, showed on the label, it touted 30% less sugar. It's using these really complicated microparticles, where we can see in this SEM image that it actually has a really complex internal pore structure. So essentially what this does is this even further speeds up the dissolution of this, which allows us to even further enhance the sweet effect using less sugar, hence the 30% less. So that was a result of creative particle engineering. So relatively speaking, particle engineering is a young discipline. It's also a very complicated discipline. So it takes into consideration chemistry, formulation science, heat and mass transfer, solid state physics, aerosol science, particles or powder science, and so on. But it also gives us a theoretical framework for rational design of particles that can have very specific properties, like the sugar particle that we saw before. But it also inherently requires a really intimate understanding not only of process, but of actual material characterization. But once we have that understanding, we can get in kind of an optimization loop here where we can engineer some really interesting particles. So current particle engineering, we can kind of consider it in two classes. We have some top-down techniques and some bottom-up techniques. Some top-down techniques are more like micronization, some of what we heard about today. So this is things like jet milling or wet milling, whereas bottom-up techniques are more so a principle of building particles up from an atomic or molecular level. So there's a lot of areas where micronization and things like that work perfectly, but then there's also areas where that is not amenable. So the rapid rise in like biologics, for example, the massive energy input we need in some of those cases, it could actually degrade the biomolecules. So moving over to some of these bottom-up techniques, we can not only find an opportunity potentially to have a technique with less energy input, there's also a lot of additional levers that we can pull in terms of like very tailored particle engineering. So the bottom-up technique that I'm going to focus more on today is actually spray drying. Don't worry, I'm not going to force everybody through a walkthrough of the entire spray drying process here. What I really want to drive home here is the idea that every stage of the spray drying process offers an opportunity to kind of drastically change the microstructure of the particle that we're going to get out of it. So early formulation decisions, what polymer we choose, solid loading, that's going to have a direct impact on the feedstock viscosity and surface tension. The nozzle design and flow rate is going to play a major role in the droplet size, which downstream is going to play a role in the final particle size. There's multiple aspects of the actual drying, like this is where the actual heat and mass transfer is being determined, and there's plenty of opportunities here to drastically alter microstructure. Even once the particles are largely formed, getting into like secondary drying, I'll show an example later of where you can actually still kind of drastically change microstructure. Ultimately, with these particles, so we're kind of blowing these bubbles, the strength and the thickness of the wall of these particles, as well as the internal pressure from the entrapped solvent, is really what's going to drive particle morphology here. And any alteration in any of those aspects can give us very, very different particles. This is just one example here where we can go from a very spherical, uniform particle to a very kind of wrinkled particle. These are going to have like drastically different surface areas, a lot of different properties, and also perform very differently downstream, most likely. So understanding this morphology and microstructure is critical. So what I'm showing here, this is actually grabbing a single spray-dried particle out of an X-ray microscopy image of thousands of particles and just kind of digitally eroding through it. So this particular particle has a history associated with it. So it's the result of everything we were just talking about before, this very carefully selected formulation, specific processing parameters. It's also going to play a critical role in the future of the final drug product. So this can affect porosity, mechanical properties, stability, and ultimately dissolution and disintegration in something like a tablet. So again, understanding this microstructure is definitely very important. So how do we go about understanding this microstructure? So there's a lot of physical characterization techniques that we can use to understand some of this, but there's a lot of internal microstructure that's inaccessible to those techniques. So imaging offers a really unique lens to be able to better understand and actually quantify some of those features. So I just want to give a really quick high-level overview of some of the kind of workhorse techniques that can be used in this particle characterization to fill in the gaps of some of the physical characterization. And then I'll just run through one quick case study, which is a nice technology demonstration of where we can use one of these advanced techniques for spray-dried particle characterization. One major technique that can be very useful here that gives us some insight into internal microstructure is a technique called focused ion beam scanning electron microscopy. So essentially what we're doing here is we're using an ion beam to very delicately cut cross-sections of, in this case, a particle. So then we can do standard surface SEM, and at really high magnifications, we can actually look at internal microstructure. This can be used as a 2D technique. So the image on the bottom right there, this is actually just selecting what we think is a hollow particle and a collapsed raisin particle, cross-sectioning it, and then confirming our suspicion that that's what we're seeing. This will often give us opportunities also to see maybe early stages of phase separation or recrystallization. Sometimes you can even see distinct domains in the walls of these particles, kind of suggesting early phase separation. This technique can also be adapted to be three-dimensional. So that movie that's playing on the top right there, this is actually a PLGA microsphere. So if we iteratively do this kind of cut image, we can actually reconstruct this into a 3D volume and fully reconstruct this entire particle. And then as with any electron microscopy technique, this gives us the opportunity to use some correlative chemical mapping. So When we bombard the surface with electrons, we're getting backscattered and secondary electrons that one detector's picking up. That's giving us these nice grayscale images, and this is where we can push into really high resolution imaging and basically probe any phase contrast distinct areas. But we can also layer on top of that where there's a separate detector that can pick up characteristic X-rays that come off the surface that are unique to specific elements. So if we have, for example, API-specific elements, we can actually map where that element is in this cross-section. So what I'm showing in the figure on the right here, we don't see any grayscale contrast of anything in this particular cross-section, zooming in on the particle wall. But when we take the, I'm not sure how well this is showing up, there's a red fluorine map there. The fluorine in this case is unique to the API. We're seeing a couple kind of aggregated regions of this that potentially could be suggesting early stages of phase separation. We can also do this technique slightly different. The bottom figure is actually showing a line or a spot profile where we can check for any types of gradients in particular elements. So again, in this case, we're actually seeing a gradient from the center of the wall to the surface of the particle in the fluorine. And then another major workhorse technique that can be used here, and mostly what I'll focus on for the rest of the presentation, is X-ray microscopy. So the previous techniques we were talking about are destructive techniques. We're actually physically cutting samples. This is actually a three-dimensional non-destructive technique. So you're imaging a particle bed kind of as it sits without actually destroying anything. And this movie that's playing, this is a 2D slice and view movie that's going through a three-dimensional volume of thousands of spray-dried particles that were scanned with X-ray microscopy. The basic principles of this are very similar to a medical CT. So like if you break your arm and go get a 3D image at the doctor, essentially you have an X-ray beam that's incident upon some material, largely based on the density of that material. It's going to attenuate or absorb a certain amount of that, and then some will pass through and we'll have a detector on the other side. And we get this image that's composed of various grayscales where, in the case of all the images that I'll show here, the brighter white something is, the more dense it is. And then the closer it is to black, the less dense it is. Like a pore or an air void is going to be black in this case. And then we repeat that at thousands of projections in a circular path around the object, and then we can reconstruct that in 3D to a 3D image, essentially. So kind of taking this to the next level, the kind of gold standard of computer tomography is at a synchrotron source. So a lot of what I was showing previously is using lab scale X-ray microscopy, which we can still press into like sub-micron resolution and get really nice data sets, but this really takes it to the next level. So with a synchrotron light source, we have a very high intensity, parallel, monochromatic, coherent beam. And this gives us several advantages over lab scale imaging. The first of these actually being allowing us to press into even higher resolutions. So we can reliably get to like half a micron with most higher end lab-based systems. With synchrotron nano CT, for example, we can actually press into like resolutions like tens of nanometers. So you'll sacrifice some field of view, but you can push to really, really high resolution. Another major advantage of synchrotron, some of the scans, like when pushing to really high-res lab scale, they can take hours, sometimes even up to days, depending on what you're doing. Synchrotron can actually take a comparable scan and bring that down to a scale of hours, or of minutes, or even seconds. So this opens up a whole new opportunity for much faster scanning and potentially even time-resolved imaging of things. And then one of the major advantages that I'm highlighting here is it introduces an additional mechanism of contrast. So I mentioned before the main driver of contrast in these other images was material density. Phase contrast, kind of leveraging that really coherent monochromatic beam, we can leverage even slight difference in refractive index of materials. So even if we have things that are very similar density, if there's just a slightly different refractive index, we can do a phase reconstruction. The figure on the bottom left here, this is just a lactose inhaler particle set in a epoxy resin. And the image A on the left, this is a standard absorption image, so using that more density-based principle. And then when we do a phase reconstruction, we can see there's an entirely new porosity or fracture network that was completely invisible in the absorption image. So it allows us to see phases that are essentially invisible in other imaging. And then the example on the right, this is comparing like a standard resolution lab scale image of a bed of spray-dried particles. Again, this is just a single 2D slice in a 3D volume. But if you zoom in on a particle, you can see how much more clear and crisp It is at a higher resolution, but even if at the same resolution, you get a much better edge detection and a much clearer picture. So this will allow for much more advanced image segmentation. So it's usually a huge leap forward just visualizing a lot of this stuff for the first time. There's a lot of unique particle classes that can arise. We see these fairly often. Even in a more like simple spray dry dispersion lot, you're typically going to see at least 2 particle classes. So we'll have these kind of ping pong like bubble particles, and then either broken fragments or collapsed raisin particles. So this will allow us to visualize these, and I'll show later how we can actually quantify that. But then this was one of the particle classes I alluded to before. We've seen this actually arise a lot with like aggressive post-drying, where we'll see these hollow particles, some people even call them pregnant particles, where they're filled with entrapped fines. In a 2D image, sometimes you'll even see these like kind of naturally broken in an SEM image, and you won't know exactly how they got there. But in 3D, what we can actually do is you can digitally slice through this, and in every case I've seen, you can always find a hole large enough somewhere that these particles can get in through. So essentially in the aggressive post-drying, it breaks a small hole, and then these fines can get inside. As you might imagine, if you don't know this class of particles exists, it can give you really confusing tap and bulk density results. Also, they can cause, kind of wreak havoc downstream too, as these aren't going to compact the same way that a standard hollow particle might. We can also have particles with like very thick or non-uniform walls. These can lead to like blend segregation or poor content uniformity, but also downstream, these are also going to compact differently. These will actually very likely survive compaction and actually create pores that are created pretty much solely from the actual spray-dried particle. And then another potentially troublesome morphology that we see a lot are these truly fused particles. So before the particle actually fully dries, if particles are kind of in intimate contact with each other, they can actually fuse together. So these, again, downstream can cause a lot of issues. These will often compact into areas in a tablet of kind of large disconnected porosity. So it'll give you confusing porosity results, but the fact that it's not connected, it won't perform the same. This will often also skew laser diffraction data. So laser diffraction is not going to clue you into the fact that these are present. And these techniques can actually all be adapted to kind of follow these particles all through the entire development process. So even before spray-dried particles, you can analyze crystalline drug substance. You can image, if you granulate, you can image your granules and do similar characterization, all the way to actually tracking the final fate of the particles in the tablet. So the movie that's playing here is another electron microscopy technique called mosaic field of view scanning electron microscopy. So we're scanning a huge cross-section of one of these tablets, and you can actually see very clearly these kind of donut structures that are actually spray-dried particles that fully survive compaction. Even if, let's say, these get completely obliterated, this again will have the opportunity to come in and put chemical mapping on top of here, and you can still get an idea of where the API actually ended up. So hopefully that gives you a good idea of the general techniques here, but now I'll just focus on that case study from the publication where we actually looked at 3 spray-dry dispersion lots, and I can show the application here. So in this study with Johnson & Johnson, the J&J team used a fixed formulation and then tweaked a bunch of the processing parameters. So we had, this was API and HPMC AS in a 1:3 ratio, which was held constant with all 3. And then we played with the feed rate, atomization pressure, inlet temperature, outlet temperature, and condenser temperature to basically get a wet, dry, and target concept of the spray-dry dispersion with the same formulation. And then this is what those images look like once we image these with Synchrotron and do image analysis. So these were imaged at 300 nanometer resolution. So we're capturing tens of thousands of particles in the field of view at ultra high resolution. And a lot of the images I was showing you before is grayscale. But where this gets exciting is when we can actually quantify things. So all the color you're seeing here is from advanced image segmentation. So we can kind of iteratively use machine learning and deep learning to basically color in every single pixel and assign it to a phase. And then we can take that a step further even and then use a technique called watershed to separate every individual particle. So now on a per particle basis, we can kind of do endless quantification. Some immediately easy quantification from there is just looking at volume fractions of some of these unique particle classes. So in this particular case, we have some of these broken fragments or raisin particles, and then true hollow particles, which basically fully entrap an air void. We can then actually quantify the volume fractions of these. So kind of as expected, we're able to quantitatively confirm that as we increase outlet temperature, we're blowing more bubbles. So that's where you see the green and red phase together. Those together comprise a hollow particle. So it's its internal void and then the green that makes up the solid wall. And then we see a corresponding decrease in the solid particles. So this if we have, like, I've seen data sets where we have every single one of those complicated particle classes I mentioned before. You can individually segment each one of those out and analyze them separately. There's also some of this data can be suggestive of some convolve features, like is there a difference in wall thickness potentially, but we can actually deconvolve that, as you see, as we press into additional characterization from the segmentation. And these results are also very consistent with what we would expect in terms of density results. So whereas we get more of these hollow particles, we're getting more air voids, and then when we have a decrease in the raisin particles, we're seeing a corresponding change in density. And that image on the right is actually just a visualization of kind of digitally pulling these phases apart once we segment them. So now we can quantify the hollow particles separate from the raisin particles on a per particle basis. We can then go in and do a very robust particle size distribution measurement. So in this table here, the red on the right, this is actually all of the phases together. So this would be the most similar to laser diffraction. But there's a couple advantages with this image-based approach where we can visually see where maybe particles are just kind of in close contact or aggregated a little bit, and we can actually kind of digitally cut them apart. So we're getting a much better true individual particle measurement. We can also, again, separate these out, and we can look at the size distribution of the solid particles separately from the hollow particles. So we can get a much more granular look at how these particles are actually breaking down. And then this slide is actually just a comparison of the Synchrotron CT size distribution with more compendial methods. So looking at laser diffraction data or even image analysis on 2D SEM images of these. A common thing that we'll see, again, when we're able to actually digitally break these apart, we're going to see like D10s and D90s go down because we're actually accounting for the aggregation and actually breaking the particles apart. But one interesting thing that you can see here is even with the 2D SEM, there's some context that can be lost when you don't have that third dimension. But when we get into the Synchrotron CT data and we actually truly break these particles down, it actually changes the rank order of some of these. So it can pretty significantly change our understanding of this bed of particles. And then I think maybe one of the most important features that we gain access to with these techniques with spray-dried particles is the hollow particle wall thickness. So once we have all of these particles segmented and separated, we can form what's called an image skeleton. You can kind of think of it in every 2D cross-section of like a midline of the hollow particle wall. So it'll be a single pixel. We can then, at every single pixel in 3D, calculate a local thickness and then get a thickness distribution. So we can create distributions of the whole lot, but then on a per particle basis, we basically know we can do like a T10, T50, T90, or an average thickness, as well as the standard deviation. This is one thing that's basically inaccessible by any other technique, and this is actually from another case study. This will almost always have some sort of downstream impact in things like tableting. In this particular case, we can see as we're dropping our outlet temperature, we're getting thicker and thicker walls. In turn, they are actually in compaction compressing less, and we're actually getting tablets with lower tensile strength. And we see this relationship often. Another interesting microstructure feature that we can probe with this is kind of deconvolving internal and external surface area. So the way that we have these segmented, we can actually assess internal surface area separately from external surface area. So a couple things that can be complicated in BET. So we have the monolayer assumption that doesn't always hold true. We have particles. It's kind of not clear what the contribution of internal and external surface area are. But in this case, we can separately assess those. This can actually be particularly useful, and we've seen in some like novel ASD techniques like co-precipitated amorphous dispersion. You can sometimes get these really wild like honeycomb type particles that can have really complicated internal and external porosity networks that can be, some are accessible to immediately to media and some would be inaccessible. And we often find when we kind of deconvolve those two things, we get results that are much more consistent with things like microdisso, where the standard surface area measurements usually give us kind of confusing results. And then this is just kind of highlighting that, so that watershed that I mentioned where we're kind of digitally breaking particles apart. This is just showing how much it can actually change surface area when you actually digitally separate these particles and include all of their external surface area, which, as you would imagine, it can, again, make a pretty big difference. So ultimately, it's definitely, I think, critical to understand all of these microstructures. We have a ton of existing techniques that we can use for this, all kind of having their advantages and disadvantages. This image-based approach is by no means meant to replace any of these physical characterizations. It's meant to be complementary, but it gives us a unique opportunity to assess some really important microstructure features, and as we saw here in particular with spray-dried particles. And then just kind of circling back to our story of a particle here, we essentially, with this imaging and image analytics, we can develop a really rich predictive design space that can be developed for critical processing parameters. And then we can also start to get a much better handle on what are critical quality attributes in terms of the actual product microstructure. And then this brings us back to that kind of particle engineering optimization loop where we can really optimize particle morphology. And then just to wrap up here, so we demonstrated here how Synchrotron CT can be used in a single imaging experiment to give us access to quantify unique things like individual particle class volume fractions, individual class size distributions, hollow particle wall thickness, and internal and external specific surface area. And then another topic for another day, but this kind of static imaging and characterization is really just kind of getting started. There's a lot further we can press into like the modeling side of things. So that video that's playing right there, we can actually take one of these data sets of actual microstructure and in the digital space kind of dissolve these and do predictive dissolution modeling. And then for anybody that maybe sits more firmly in the experimentalist camp, the advantage I mentioned of Synchrotron where we can image things really, really fast. If we are having processes that are happening like in a tablet, like a gel layer formation or something like that, we can actually time-resolved image that and physically watch and quantify microstructure as it evolves. And then with that, I just want to acknowledge my collaborators and colleagues at J&J Innovative Medicine, DigiM, and University of Ghent, and happy to take any questions.
Thank you, Phil.
Applied this to modified release coating?
Yes, that's where the model, yeah, we have very well-developed models for that in particular. This technique is basically amenable to any dosage form.
Can I see inside a tablet how excipients are distributed? You know, let's say if I have a disintegrant,
Yep.
tablet to tablet, see if there is any value.
We did a recent publication with Genentech where we quantified that exact thing. So we took one of those mosaic field of view images that I showed. We were able to segment out the cross-caramelized sodium and get a distribution of it and then correlate it with some of the disintegration.
Okay. So maybe I need that publication.
Yeah.
Thank you.
It was a great talk, thank you. I was curious, have you ever looked at like the percentages of like hollow particles and solid particles on the effects of downstream secondary drying? Like either the time to post-dry or the level of solvent you can get to with different percentages?
No specific case study comes to mind, but we absolutely could. Like that would definitely be a great application for this, for sure.
Cool, thanks.
Any additional questions? No. All right. Thank you again, Phil.